Welcome everybody to Lecture 2, Information Retrieval in the summer semester 22-23. Due to global warming, there are now 2 summer semesters, one in the summer and one in the winter, in case you didn't know. So I have prepared another exciting lecture for you today. We will first say something about your experiences with the first exercise sheet, which was about the inverted index. There's another Q&A because there's a holiday next week, so you have 2 weeks for the next exercise sheet, and so the Q&A will be not this Friday, but Friday next week. So please come if you have any questions or problems. Just realizing that I have trouble figuring out where to look at the camera, at you, at this screen, at this screen. So right now I have to commit to where I look at. And then we will talk about ranking today, evaluation, and the exercise sheet will be something I will talk about as we go along. So first, your experiences. So most of you found it an interesting exercise, a good start, quite doable. Welcome opportunity to refresh your rusty programming skills, and there are a few with more problems, and I have a slide for those too. Here are some quotes from your experiences. Thank you for giving us feedback. It's always very valuable to have. Good start, hands-on experience. Yes, that's what the whole lecture is about. Coding abilities more rusty than my bicycle chain. Yes, very. I think many of you had that problem, but many of you said, yeah, it's a little bit rusty, but that's a great opportunity to refresh. Another comment in this, the 2 cool alarm sounds, indeed. And it should be mentioned that Python is a prerequisite. I wouldn't say it's a prerequisite. I mean, you don't have to use Python, but it certainly helps, and maybe you can use it as an opportunity to learn it. You should certainly know some programming language at this point. I have an important slide for those among you. There are 10% or so, and that's just normal because everything in life is like a normal distribution, who have more problems than usual, and we can read it from the comments. So about 10% for whom already this first relatively simple exercise sheet was a lot of work, and I have a slide for you and some messages because I think it's important. We completely understand it's not pleasant to be among those 10% who have it hardest. But yeah, that's just life, that there are these 10%. I want to emphasize that we are very happy to help and support everybody, including those who have more problems. And here's the but. I mean, this is really important. If you want to stay, and you're welcome to stay, I think you just have to accept that it will be more work. I mean, we can't, the amount of work and everything and difficulty, it's just adjusted to the 80% or so in the middle. So it will be more work for you, but I mean, you can accept that and say, yeah, I have more problems due to whatever reasons, personal circumstances, maybe I'm missing something from earlier lectures which I now have to learn, that's okay, but then you should just calculate with twice the work or twice the time or something. I think that's really, really important. And it's also important because there's a strong correlation. I see it in what the feedback you give, the quality of the exercise sheet, between difficulties people have and when they start committing something to our SVN. And the latecomers are always often those which have more difficulties. So if you have trouble, what was that? Ah, the Windows, okay. You should start on time. The more difficulties you have, the earlier you should start, and you should reserve enough time. Yes. And we welcome your feedback, but please don't blame us, but tell us how you're feeling, how we can help you. Please don't tell us what you think we are doing wrong. I think especially if you have difficulties, that's the wrong approach and not very helpful. So I hope that helps. And now let's go on with the feedback to the exercise sheet. So it was about a first very simple search engine, and the master solution is online now. So here it is. There's just one sheet now for the first one, it's there. Here's the master solution. Everything is perfect. The tests go through, check style errors, none. And let's just, I've tried this already, try it out on the movies data set. So that was what the first exercise sheet was about. You started, and now you can ask queries. So I don't know, maybe we are looking for the matrix queries. I type matrix, and now I get 3 queries, the title and their description. We see the first one is the matrix, the second one is not the matrix, but it's a movie which mentions Keanu Reeves, who also played in the Matrix. So that's something which you frequently encountered, and it was also part of the exercise sheet. Play around. When you talk, it's very loud up here, so I think you should not, otherwise it's too loud. Thank you. So here are some examples. So the sheet was to figure out what works well, what does not work well, and why. So this is an example of a query that works very well. Why does it work very well? Because it's 2 words which are extremely specific. I mean, Shawshank probably occurs in no other movie description except in that of the movie. And it's the most popular movie. So if it matches, it will be number 1. Nolan, there's no, if a description mentions Nolan, it's Christopher Nolan, because it's not an English word otherwise, and it's such a unique name. So these things worked well, you figured that out. Pokemon works super well because of the accent aigu, and super specific. Lord of the Rings, that's interesting. Why does that work? And it was a really good exercise because there were obvious things, but also subtle things. So let's try Lord of the Rings. And note, Lord of the Rings, of, super frequent, the super frequent. Lord is also not so specific. Rings is also not so specific. You have lots of movies with rings, yet the first 3 are exactly Lord of the Rings movies. And why is that? It's not because you can see it here in the highlighting, the words occur so frequently, but it's just because the movies are so popular in the ranking, right, that you get them first. So in this case, the words are super unspecific, but because these are among the most popular movies, you get them first. And here are examples of other movies. 2001, you don't get it because we didn't index any numbers. And in practice, when you see other search engines and you get angry, it's usually because they're making these stupid mistakes like not indexing certain words, so you don't find it. Titanic. Titanic is not so popular as other movies which also mention the word. Harry Potter has the same problem. We could try it out. Here's an example of a word you forget the accent aigu and you don't get the hits and so on. So you figured all that out, and as I said, obvious things, but also many subtle things. Okay, this is just one general comment. One little twist compared to the lecture was that when in the lecture, what I did was when you have a word occurs in document multiple times, you just have it in the inverted list, the document, the record ID multiple times. And I had that to show you Zipf's law. In the exercise sheet, you were not supposed to do that. That is, if a word occurs multiple times, the record ID should appear only once. And the obvious way to do it is this code. So if it's not already in the list, append it. If it's in the list, don't append it. What's the problem with this code? Who can tell me? I mean, innocent looking code, looks natural code. What's the problem with it?
Basically doesn't run in linear time, and then because the data set is huge, it takes a lot of time.
So what's linear time? So the not in?
Yeah, it's not. So the not in is basically like another loop in Python.
Yes. Yeah, thank you. That's exactly it. So let me repeat it for everybody and also a Zoom audience. So the if condition, not in, that's searching in whatever you already have as inverted list, which might already be very long. not in does not know that it only has to search at the end for whether the word is already there, but it will search the whole list, which means as you go along and you are inside a loop, you are, for every addition to the loop, you will search basically the whole inverted list that's already there, and that gives quadratic behavior. So hidden quadratic behavior, it happens so often. And that's what's written here. So here's a super important piece of advice, because there were already questions about this. Can I use this function? Can I use that function? There are two aspects here. One is, of course, you shouldn't use built-in functions or library which solve the whole exercise sheet for you. That's number one. But number two is, when you use functions from a library, you should always ask yourself, what am I doing here? What's the time complexity? And this is an example of natural use, which is just terrible. And you see that a lot in code, also in code from products, companies, and so on. So very, very frequent problem. So let's look at the chat. We have some questions there. By the way, you're very welcome if you use the chat, also people in the room, for asking questions in between. Maybe Natalie answers them, or somebody else wants to answer them, or I answer them. So people on Zoom use the chat, everybody in the room can use the chat. We can just do it in parallel. So that was the introductory part, about 10 minutes as planned. Now we go to the first part of today's lecture, which is about ranking. We completely disregarded ranking. I mean, what we did here is you just, many more hits, you just output those which come first in the input file, which was already not that bad because the input file was sorted by popularity, but we have already seen there are problems with that. So the motivation is obvious. You have a lot of results, often millions if you search on the web, and you want the most relevant ones first. And the question is, how do you measure what's relevant? Relevant, if you think about it, is a very ill-defined and also subjective notion. What's relevant for my query? My search engine has to guess what I want. So here's the basic idea. So the basic idea, so these are our inverted lists. And here I have two different ones, University and Freiburg. This is what we had so far, the blue things, just the IDs of the documents or text records containing that word. And now we also have a score, something between 0 and 1, doesn't have to be, but let's do it like that right now, which somehow says it says something, we will see in a second. And when I merge these lists or intersect, today we will merge, I will just sum up these scores. So for example, let's look at 53. 53 occurs here and there, 0.2 and 0.1, so it's 0.3. So by aggregating, now aggregation, I deliberately wrote aggregation, but here sum. Yeah, but it could also be something else. Doesn't have to be sum. Could also be the average or maximum, or somehow aggregate them. If a document only occurs once, like 17 does not occur in the Freiburg list, it's still in the result list, but then just with a 1 score. And then we sort. Now we just sort by the scores. So now 127 is first. Why? Because it has a large score in both lists. Yeah. And now one important thing to note, and let me just write this here. Note. A document which, let me just write it here and say it before. A document containing only one of the two words, like, and this is something we didn't have last time. And for example, where's a document which contains only, and what I want to say is that it can be ranked pretty high. What's the first document in the sorted list that contains only one of the two words? 34, yes? Like 34. Like number 34. Can be ranked higher. Than documents containing both words. And that's very important. And I'm writing that up so that you have some time to think about it, because it's really important. Words, I have to write them again because something went wrong. And it's something which, for example, Google didn't do until about 10 years ago. So you might think that's obvious, but as soon as you do that, it becomes risky. Now you're omitting some words, you have to omit the right words, you get a lot more hits. So in the first 10 or 20 years of web search, depends on when you start counting, search engines would not do that because it was too risky. But here, when we merge, and we do that from now on, we do it. So here, these entries, they're now more complex. It's a doc ID and a score. We call them postings. For whatever reason, it can also contain more information. So this is now a whole record. For example, it could also contain the information where the word occurs in the document, at which position, can be more than one position. But for now, and for I think for most of the rest of this course, it will be just the document ID and some score. Okay. So how do we get, that's just a small remark. So this is merging. This is basically the same algorithm as last time, which we used for intersect. With a very small twist, you can turn it into a merging algorithm. You just also write out the things which only occur in one list. It will be part of the next exercise sheet to implement it, but it's really only one line or two change in the code. So you get this merge list. How do you get the sorted list? Well, you sort it. So that takes n log n with a typical sorting algorithm. Typically, you only want to display the top k hits, like the top 3 or so. So then you can do a partial sort. And a partial sort is faster than a full sort. If you only want the top k in sorted order, that works in n plus k times log k. For example, one popular sorting algorithm is a heap sort, where you put everything in a heap, in a binary heap. That can be done in linear time. If you do it carefully, watch the algorithm's data structure lectures. I explain it there, or Fabian also explains it there. And then you just pop from the heap. Just give me the smallest, and a heap operation costs log n time. You do it k times, so you get this running time. And there are also, you can also modify quick sort, so this recursive divide and conquer thing to get that complexity. So it's linear plus k times log n, which is for small k much better than n log n. Yeah, in particular, if you have constant k, it's linear and not slightly superlinear. You don't have to do this, but maybe you have fun doing this, then you can implement it a little faster for exercise sheet 2. But just so you know. Now, where do these scores come from? Here I just wrote some scores, and that's what the rest of this first part will be about. Where do these scores come from? What are good scores? Why does it say 0.8 here and 0.1 here? Well, there we have them again. What the score should somehow measure is how relevant university occurs in document 17. So how relevant is it? And think about what I showed you earlier, for example, when I Matrix. That was a good example. So this is The Matrix, so it's the first movie about the Matrix. And every mentioning of Matrix here is very relevant for what this document is about, right? This document is about the movie, and this talks about the movie. If you take the second movie, it also mentions Matrix here, but the word matrix is not really relevant for this document. It's mentioned here in passing because Keanu Reeves is in that movie and he also played in Matrix. So this occurrence of matrix is much less relevant in this document than here. It should get a lower score here compared to there. And here you already see a hint how you could do it, which is not always true, but that's one heuristic to do it. Matrix here occurs a lot of times, right? And here it occurs only once, which is one indicator, and which will indeed be our first heuristic. Just look at how often does the word occur. If it occurs really often, then probably the document is about it. Okay, so term frequency. That's the simplest heuristic and the first thing we do. And here's the problem with that. So let's do it like that. So here we have a term frequency count. So what it means now, in document 57, whatever it is, the word university occurs 5 times. Word Freiburg occurs 3 times. The word off, which doesn't mean anything, occurs 14 times. In document 123, it occurs 23 times for whatever reason. It's just a preposition, right? You have a lot of offs and the. Let's just see that again so that it's super clear. The Lord of the Rings. Yeah, I mean, everything is highlighted here. You have a lot of the here, of course, when it mentions the Lord of the Ring, but also the of the, these are just frequent words, right? They just occur. It doesn't really mean anything how often they occur. But now, let's just do what we did earlier with these scores. Now let's just sum them up. So for document 57, we just take these as scores. 5 plus 14 is 19, plus 3, 22. 2 plus 23, 25, plus 1, 26. So now, this document gets ranked before this document. Right? But if you look at it, 57 occurs these meaningful words, university and Freiburg, much more often than these, the meaningless one off. So actually, it looks like 57 should be first, right? And not 123 just because of off. That's the point of this slide. And this is what we solve now. What we now look at for each word, we also try to figure out, is this a word which means a lot or just a fill word like off the, which occurs everywhere? That's actually an easy way to do it. You just count for every word. In how many documents does it occur overall? So for a reason that will become apparent in a second, I'm taking powers of 2 here. It doesn't have to be powers of 2. It's just so that my example calculations give a nice result. 16,384. Every computer science student should know this number by heart. It's 2 to the which power? $14 maybe. Other opinions, other. So let's start with 1024. 1024 is also a number, every compute. It's 2 to the, it's 2 to the 10, which is very useful if you want to convert between powers of 2 and 1 million or so. 1 million is 2 to the 20 approximately, because 1000 is approximately 2 to the 10. So if this is 2 to the 10, and this is just 2 to the 14, yes. How about this one? You can also deduce it. By the way, doing these calculations in your head is great for math. 19, yeah, because 1 million is 2 to the 20, so you can come from that side. Very good. So we have 2 to the 19 here, and we will use that in a second. So university, Freiburg is super specific in my example here. University is mentioned more often, right, because there are a lot of universities. And off, it just occurs a lot. Let's say we have 1 million documents, 2 to the 20. And now what we compute is inverse document frequency. Inverse document frequency is just if a word is very frequent, I want it to be small. Let's just look at ID of off. So, and let's just write, let's first take this one. Off occurs 2 to the 19, and here we have 2 to the 20, so that's log, if we take the formula which I've written there, log. Do you have a question, or are you just somebody? So this is log 2 of, I think somebody should mute their microphone. Or can you mute them? I think you can find out who it is. So the formula is log 2 of number of documents, which is 2 to the 20, divided by how often does this word occur, 2 to the 19. 2 to the 20 divided by 2 to the 19 is 2. Log 2 of 2 is 1. So it's really small. Let's look at Freiburg. So this will be log 2 of total number of documents is 2 to the 20 divided by, I divide by the frequency, which in this case is 2 to the 10. So it's log 2 of 2 to the 10, it's 10. And let's also do it here, university. We have 2 to the 20 documents. It occurs in 2 to the 14, so somewhere in between. 2 to the 20 divided by 2 to the 14, 2 to the 6. Log 2 is 6. So you see, and now if you just look at these numbers again, just as numbers, 6, 1, and 10, then what this says is this is a super frequent word, ignore it, so a very low IDF. This is a super specific word, Freiburg, so it gets a relatively large number, and university is somewhere in the middle, so it gets some in the middle number. And now we just, why do we use the log 2? That's an important thing, which we will see again on a later slide. If you would use these numbers directly, the differences are just too large, right? I mean, here you have 500,000 and here you have 1,000. It's just the difference is too big. You somehow want to dampen the difference, and when you want to do that, you often use the log 2. There are also theoretical reasons for those, but we will come back to that later, but not now. You just look here, the difference is a 6, 1, 10. Still a difference, but not so big, right? Here the difference is a factor of 500. That's too big. Now let's just use these words, use these scores. And let me just write down the IDF scores again, so that so our IDF of, what was the first one? University was, let's play a little memory. 6, very good. 6, IDF of off was 1, very good. IDF of Freiburg was 10, perfect. So those were the numbers, and now let's just use them here. Yeah. So these were, this was our TF example, exactly, and now we have our, so let's also write it here, how we got it. So this is now 5 times 6, right? 30 is 5 times 6. That's just a TF score times university, and this is just 14 times 1. So you see, we have this high number from the frequency here, but now it gets only multiplied by 1. You see what's happening. Here we have 3 times 10, so Freiburg occurred only 3 times, but it's a very important or meaningful word. So this is 3 times 10, and here we have 2 times 6. 23 was a large frequency, but now multiplied with a small IDF. And here we have, it only occurs once, but in a very meaningful way, 1 time 10. And now we sum up the scores, and now, as it should be, 30 plus, this is 74, this is 45, and now 57 will be ranked first. And that's the whole point of TF.IDF. And I spent quite a bit of time on this, because TF.IDF and its variations, it's probably one of the most important scoring formulas. You do not only find it in search engine context, but whenever you are in a context where you want to rank stuff, You will use something like TF.IDF. It's a simple idea, but a very fundamental idea. You take frequency on the one hand, and then something like invert document frequency to tell apart features which are more important from features which are less important. So now comes a refinement. So here are some problems when you use that in practice. The IDF part, let's just say it for now, is fine. This can also be refined. The TF part has some problems. Here are 2 problems. Now assume a document is longer, let's say twice as long. If a document is twice as long, it will contain every word twice as much on average, right? So that's kind of unfair. You have maybe the word matrix occurs in some document twice as many times just because the document is longer. You have short documents, you have long documents. You should somehow take that into account, especially if you have documents of varying length. And now there's another thing. If they have the same length, and that's similar to these large numbers which we have seen for inverse document frequency. If a word occurs twice as many times, maybe then the word is a little bit more relevant for that document, but maybe not twice. Maybe that's too much. Maybe just 1.2 times. Right? That's very similar to what we have seen here. So yes, off is more, that's the same rationale as here. It's 500 times more frequent, but it's not 500 times less important because of that, right? We should dampen this somehow. We did it with the log2 here, and that's a similar thing we want to do now. And here's a formula which does that, which I will explain now on the next 3 slides. And this is a variation of the TF.IDF formula, and I just replaced the TF by a TF star, and to be precise, by this here. And we will now understand this funny formula. And this, you will also use it in the exercise sheet. So it's now TF like before, but multiplied with something. We don't have to understand it now. There's a K here, there's an alpha here. We will now understand why we do that. So this DL is the document length. Average document length plays a role, and B and K are just parameters. Then there is some magic settings. If you don't know how to set them, you will play around with it for the exercise sheet. Set them like this. Let's just look at 2 special cases to understand the formula a bit better. So if you set K equals to 0 and B equals to 0, so if you set B equals to 0, then this alpha value will be what? What's this alpha here, whatever it is, if you set B to 0? I'm confused. There's something wrong with this. There's something wrong with this. Yes, I want to keep my ink annotations. This is not supposed to be there, right? Yeah, this was a copy and paste error because of last minute changes. And Frank, I don't know if you are listening, but it's still super slow, the machine here. So, alpha is what for B equals 0? 1, yeah, that's correct. That's equal to 1. Okay. So for, and then we have TF star is just TF, and let's write it like this as a fraction, K plus 1 divided by K plus TF. So if we have K equals to 0, what we will get is TF star is equal to TF times 0 plus 1 divided by 0 plus TF, which is just TF divided by TF, it's 1. Which, this is what we did in the first lecture, right? Whenever the word occurs, we just count it as 1. We don't differentiate between different frequencies. So let's now look what happens if we let K go to infinity. So that's TF times K plus 1 divided by K plus TF. Now how do we do that? Well, now we have K goes the denominator, numerator and the denominator go to infinity. Let's just have to write at the bottom, that's always a little bit harder. Let's just divide both of them by K. So here we have 1 plus 1 over K. I divide the numerator and the denominator by K. And here I have 1 plus TF divided by K. Okay. And now you can tell me if K goes to infinity, 1 over K goes to 0, TF over K goes to 0, and this will be just TF. Yeah? So this TF star, the larger you choose K, the more it will be the normal TF. Any questions about this for now? Okay, and now let's, why this formula? Now I want to explain why this strange formula, where does it come from? Here, and I will do it this way, I will now name 3 properties which I think are pretty natural to have, and then I claim that's just the simplest formula which has these properties. So what's a natural property? You want to replace TF by something. If TF is 0, then your modified thing should also be 0. And let's just verify this on the, so let me write my formula here again. So that's TF times K plus 1 divided by K times alpha plus TF. So if let's just, if this is 0, K times alpha plus TF is, if this is 0, well, let's look at this part here. This part is not 0. I mean, this is not 0, this is not 0 for for at least for the non-binary case when K is greater than 0. Yeah, so this whole thing can only be 0 if the first factor is 0. So that's pretty easy. Okay. Now, you want to modify it in a way, we already said this, you somehow want to dampen the effect of, if you have twice as many occurrences, then you want this modified thing not to be twice as large, just a little bit larger, but it should still increase, yeah? It shouldn't be worse if the word is mentioned more often. So let's just look at that. Why does TF star increase as TF increases? Let's just verify this for this formula, and let me maybe write it down here so that it's not so crowded. Let me put a marker here and argue here. So how can we see, and I can tell you these are popular exam questions. So TF star, let's just write it again. It's TF times K plus 1 divided by K times alpha plus TF. And now we are wondering if TF increases, what happens to this? Now TF occurs here in the numerator and in the denominator, and that somehow makes it hard. So let's just divide both by TF, and then it becomes a little bit easier to see. So we divide by the TF. The TF is like it's up here in the numerator, and now we divide by TF at the bottom. So what we get is K times alpha divided by TF plus 1. And now we have it only once in that formula, and so, yeah, now it's in the denominator, And there it's again in the denominator. So if TF increases, the whole thing increases. Here you can see it, yeah. So let's just, yeah, increases as TF increases. And please do ask if it's not clear or if there are any doubt. Yes? Yes, but it's in the denominator of the denominator. Yeah, it's divided by, maybe I should have written that more clearly. So it's something like, yeah, let me just write it here in a simpler form. You have something like 1 over 1 plus 1 over x. So now if x increases, the whole thing increases. It's the denominator, but in the denominator it's again the denominator. Yes. And there's still problem with system resources on this machine, which is why the writing is slow. But we will cope with that. So now let's look at the third property. If the term frequency goes to infinity, becomes larger and larger, our TF star shouldn't become larger and larger. It should hit a fixed limit. Let's just verify that it does that and figure out what the limit is. So now we want to find the limit for a term that occurs super frequent of, and same formula here, TF times k plus 1. I'm sorry for the delay. It's also a little bit annoying for me, but I can't help it. Now we have the same problem. We want, yeah, we have the TF in the numerator and the denominator. It goes to infinity, but we can do the same thing. And let me just write it again. TF goes to infinity. And let me just use the same formula here as above. And then you can see what happens. K times alpha divided by TF plus 1. Well, and now you can see what happens. This goes to 0 because it's divided by TF, 1 TF, and then you have K plus 1 plus 1. So it's K plus 1. So this formula, which we have seen before, goes to K plus 1. So that's essentially the meaning of the K parameter. So it essentially says, determines the limit. So you want to have, let's just recall these three properties again. Whatever you replace the TF with, it should also be 0, only if the TF is 0, very natural. It should increase for a word that occurs more frequently, and if the word occurs super often, it shouldn't go beyond a certain limit which you set, which is a parameter. So here we have the standard setting 1.75. That says, however frequent a word occurs, the TF star will be at most 2.75. That's what it says. And yeah, now you want a formula with these properties, and that's as simple as you get. I mean, that's just the simplest formula. You tell me if you come. This is not a proof now that this is the simplest formula, but yeah, it's a simple formula, and if you want to have these three properties, don't think you can do it with a simple formula. And we have an alpha here. What does that mean? Well, I can have an alpha here, and let's just see how we can make use of that. So if I can put any number alpha here, and I still have all these three properties. So we have a free parameter, which we can also put to good use. That's what the second slide is about. How do we use that parameter? Well, let's rewrite this formula again a little bit by just doing it like this, by dividing by alpha, again, both numerator and denominator. Then we get TF divided by alpha here. And here we have this divided by alpha is K, and TF divided by alpha. So what we have is, it's like replace TF by TF over alpha. So it's like normalizing the TF. If alpha is 2, just divide the term frequency by 2. That's the effect of the alpha, dividing the term frequency by something. And this is, so what is done by this BM25 formula, how the whole thing is done, is you normalize by the document size. You compare the document to the size, to the average size of a document. So if a document is twice as long as, is that myself or somebody else making these noises? So if a document is twice as long as the average document, then this thing here would be 2. So you could just say, okay, it's twice as long, so I divide the turf frequency by 2, but that's a bit too extreme. So you do this thing, which is some in-between thing. So if you set the B to 1, it would be exactly this extreme case. If you set the B to 0, which we have seen earlier, alpha is 1. And then it's the, let me maybe also write it on the formula in case, yeah, it's not here. So for B equals to 0, you don't normalize. And for B equals to 1, you do the full normalization. Then you have dl over average dl, and you typically do something in between. We have seen an example B. So these are 2 parameters to play around with, K and B. That's the formula. It's amazing if you go to the literature, how much literature you find about theory behind the BM25 formula. I don't find it very convincing. It fills a lot of pages. I think these 2 pages, you don't find that anywhere. I haven't seen that in the textbook so far. For me, that sums it up, why this formula is so successful. Why did I pick that formula and why is it called BM25? It's because these people or other groups working on it, they tried out a million things, and then one of these formulas, they had all these different names for this formula. This formula was called best match, and they probably had versions of it like BM1, BM2. It's like the programming language C, right? It's the successor of B. And there's also D. So yeah, that's how these names come to pass. So some class of formulas, and then the 25th iteration somehow worked, and this became famous. At the time, pretty long time ago now, all the competitions, these search engine competitions, many years in a row, always this formula won, which is why it gathered some fame. And if you ask me, these 2 slides, which I've shown you here, they explain why this formula, yeah, you don't find it in textbooks, but you find it here, why it works. Okay, so that concludes almost the first part of the lecture. You're very welcome to ask questions. Just some more minor remarks now. That's not minor. You should implement this. So how do you implement yeah, so you should, let's go back to the slide with the score. Oh my, this always takes, yeah, here's the formula. So you should now use scores, and you should use these scores here. Now how do you do that? So every document should now get a score, and you should compute with these scores. How do you compute these scores while you build your inverted index? And that's what this slide is about, which I will go to now. Well, think about it. Let's first ignore the IDF. Computing the TF scores is something you can do while you build the inverted index. You have done the first exercise sheet, right? You are adding, you are going through a particular document, and now you see the word the first time in that document, you see it the second time, the third time. What you did for the exercise sheet, you just did, oh, I've seen it already, I don't append it again to the inverted list. Now you can just have a counter, oh, I've seen it already once, now I've seen it a second time, increase the counter by 2. Now I see it a third time, increase the counter by 3. So this you can just do while you construct the inverted list. Very small modification in your code. But now you only have the TF. So now you did what you did for exercise sheet 1. You have the TF scores. The nice thing is the TF.IDF scores is just some function of the TF scores. And while you're doing that, you can also compute document length, average document length. That's easy. You see a document, you just know how long it is. If, yeah, maybe Let's see if it grows louder, we have to close the door, but maybe not for now. That's also easy. Now the IDF scores, how do you do that? Well, what is for IDF, you need the DF, the document frequency. Document frequency is just how often does a word occur in a document. That's just the inverted list of a document. Let's just go through an inverted list again. Here we have it. Yeah, let's say that's the complete inverted list of university for whatever document collection that is. So that means university is contained in documents 17, 53, 97, and 127, which means there are 4 documents containing university. So it's just the length of the inverted list. Inverted list length. So very easy. You have compute your inverted index, and now the length of each list just gives you... You want to close the door? Yeah, it's a bit annoying. Thank you. So that's it. When you will code it, it will become clear. So in the first pass, you compute the TF scores. In the second pass, you easily get the DF. And if you have the TF, the DF, and the document length, you can easily compute that formula. That's how you do it. This is not needed for the exercise sheet. You can do it, but you don't have to. So what you should do for the exercise sheet is play around with the parameters, K and B. That's what the sheet is about, and we will look at this more in the second part. You can also do other fun stuff, like if a document contains all the query words, they don't have to now. Maybe you want to boost the results. Say, yeah, it doesn't have to contain all words, but if it does, then it's even more relevant. I give it some boost. But only boost it. You have seen it for exercise sheet 1. When you restrict it, you say all words must occur. You're making it too hard. Some relevant results will just fall out. Take the popularity into account. The BM25 formula we have seen is purely about term frequencies, how often terms occur or not occur. Maybe you should want to take popularity into account. So we give you a lot of numbers. They are sorted by popularity. We give you a number of votes, IMDb rating, Wikimedia links, and so on. Note something here. When you have... let's just look at this again. When I go to the data set here, let's just look at it. Okay, I have to go to the end, I think, oh yeah, I have to go to the end a lot. Maybe let's just cut out the cut F1, 3. Let me just cut out the abstract. 3, 2, 4. No, 3, 4, 5. That's what I wanted, right? I'm just cutting out the... What did I do wrong? Minus. Thank you. Now I just have the titles and the scores. So this was number of IMDb votes, this is IMDb rating, and this is a number of Wikipedia links. The rating is like a good score. You could take it immediately as a score because it's between 1 and 10, like school grades, right? This is a number of the kind which we have seen earlier. Number of votes. Some movies have millions of votes, others have 10 votes. That's too big a difference. You need to dampen it somehow if you want to use this. So a typical way to do this is to use log in some form, as we have seen earlier. You don't have to do this, but you may want to do it. You may want to somehow refine your formula. Anything else that comes to your mind? So we have a little competition. Maybe that's the right time to show this. Yeah, we can just go here and go to the exercise sheet. Yeah, maybe that's now the right time to show it before the break. And timing is perfect, I think, until now. So the exercise sheet is just redo exercise sheet 1. And I should say redo means take your own code and pimp it up to add the BM25 scores, but you can also just use the master solution and proceed from there. So that's the first exercise sheet, extend your inverted index by BM25 score. This is what the second part of the lecture will be about. You have to evaluate it, and now you should play around with your scoring function and try to be as good as possible. And the second part of the lecture will be about some measures, measuring how good is what you have done. And you should try, everybody will post a row here, and you can just try to get the best result. So it's like a little leaderboard here, a very simple leaderboard. There are totally other methods which we don't talk about here, which are out of reach also for the second exercise sheet. So one thing that's of course super important if you have a real search engine is analyze what users actually query, which queries are popular and what they click on. I mean, we can't do that here because we don't have that data. Obviously important. And another thing that's also a big topic, you can use machine learning to learn good rankings. I mean, that should be obvious that it plays a role here. If we just look at the formula, this formula has some funny factors here, like K and B, and how do you set K and B? I mean, these could be learned. I mean, that's one thing, you could learn these factors, but you can also learn much more, not use a fixed formula, but learn the whole ranking altogether. That's called learning to rank. That's a big topic. We will not deal with that at this point. So let's make a break here for 5 minutes or so. Before we go into the break, any questions from your side right now? You can think about questions in the break. Yes, please.
Yes, I assume that it might be, depending on the data, if it's better to use a different function to compute the inverted IDF.
Yeah.
We use log2, but I assume, is it right that sometimes it might be better to use division by 10 or log3 or something, or is it like very strictly use log2?
Okay. This is just about the base of the logarithm. So the question was, does it depend on the collection, whether log2 is good or some other log is better? This can be answered with, if I find whether you take, to whatever base you take the log. So if you take a log of something to the base of b is just the natural logarithm or any logarithm of x divided by that logarithm of b, which means if you choose a different base, then it's just a constant factor for everything. It's like all the scores are multiplied by 2, which doesn't make any difference. Now all the scores are twice as large, but because it affects all the scores equally, the ranking will not be affected. Which is actually an important point, which I come to back later. The absolute values of the scores don't really matter. It's just the relative order they imply. So which means the base of the logarithm is immaterial. It's just 2 for convenience. Any other questions right now? Yes?
So if the keyword is in the title, for example, shouldn't it mean more than just having it in the description?
If the keyword is what, for example?
Is present in the title of the movie.
Yeah, that's another idea which was not on the slide. Exactly. That's like the boosting idea can be very valuable. Like say it's in the title, that's more important. Then you immediately get into the area of spamming, but we don't have spamming. If you do that on the web, the early web engines did this, and then of course all the porn sites put all kinds of words in the title so that would be first and so on. But we don't play that game here. So that's the problem with boosting functions. You can immediately abuse it to get your documents higher. But yes, for the exercise sheet, you're welcome to try these things.
So how would you actually measure the quality of your ranking?
Yeah, how do you measure the quality? That's what the whole second part is about. Yeah, exactly. Very good question. Okay, let's have a break now. If you have more questions, you can ask them later, 5 minutes. So let's continue with the second part. And there was already the question. Yeah, but that's what the first slide is about. Is it? Yeah, maybe. Yeah, I mean, the question is, what's the motivation for the, I hear you talking, what's the motivation for the second part? Now you're playing around with these parameters, how do you find out for what's actually how good? I mean, one way to do it, how people often do it, let's just go back to, you have your program. Maybe let's start with that. You have matrix, it works okay, 2 matrix movies are there, the second one should not be there. So what do? You play around with your method, you try your query again, you see, oh, now I have the 3 matrix movies, okay, perfect. But now it's only for 1 query, so maybe you try it on 3 more queries, so that's how you would do it, right? You have some queries, you try it out on these. And this is essentially what we are doing now more systematically. So that's what evaluation is about, and it's of course super important for anything really, but in particular for search engine work. So we need the ground truth where we have a number of queries and what we want to have for these queries, the relevant document. For example, the query is matrix movies. Let's assume it has this word here, which doesn't carry any meaning if you have a collection only about movies, but still, user typed it. And there are 4 matrix movies. Is it still 4? Is it 5 in the meantime? I'm not sure. And let's say they have these IDs, so line numbers in our collection. And that's what we have in our file. Let me just show you this. So we have prepared, and that's actually Natalie has prepared quite a lot of work. And very important work. It's also on the slide. So we have prepared 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 queries. So films directed by Steven Spielberg. And I think I should use another. Yeah, this is better. So films directed by Steven Spielberg. Here they are. So that's the complete list of movies directed by Steven Spielberg. No, it goes on here, so there are more of these, yeah. James Bond movies with Daniel Craig, there are 5 in our collection, and so on. So they are also, films about Batman. So somebody might just query Batman films, right? And you will see it on the exercise sheet. You actually don't have to take that as query, but it's also part of what you can do is to pick the query. Maybe you don't want to query films about Batman, because about doesn't mean you just want to Batman, for example, or Batman movies or whatever. Anyway, this is the query. You can figure the description of the query. Here are the relevant documents. So that's the ground truth we give you. So we did that for you because it's a lot of work. And we have built a ground truth for 22 queries. I've shown you only half of them. That's also important. There will be a later slide on this. The training, ones for training and the ones for testing. Here, very similar ones, and we intentionally did them in a parallel way. So here you have films by Steven Spielberg, and here in the testing one, you have films by Stanley Kubrick. So they are parallel in that way. Why is that important? Let me tell it now and again later, because it's so important. When you do all your tuning and trying out stuff, just look at the training data. You're not really doing training in the machine learning sense, but you're doing training in a human sense. Like you are developing and tuning your system based on something we give you. You play around with, you try to be as good as you possibly can on these queries here. Then in the end, you should not evaluate on what you were tuning to for hours. You should evaluate on something else, so that what you did is actually meaningful. I have a slide about that, a separate one, because it's so important. But that's why we have 2 ground truth sets, one for training, one for testing. So, and now the question is, how do you evaluate? How do you use this for evaluation? Yeah, and this is called a benchmark. If you have something, look, here are some queries or a basis for queries, here is what should be the ideal result. So now you need a measure which somehow your program runs on these queries, does something, and now you want a number which says how good did it do. That's like the simplest one here, precision. And let's just do it together. Precision at 1, at 2. Let's just make a start. So here we have a result list. Here you see the 5. How do I do this? So 5A2 is, so this one is relevant. This one is not, this one, 17 is not relevant. This one is relevant. This one is relevant, and this one is not relevant. So let me do this in red here. So not relevant, not relevant, and not relevant. And you will compute bits about these numbers. So your search engine, you gave it matrix movies, it has computed this result list where the first one is relevant, the third one and the fourth one, and the other ones not. Now precision is just look at the first position. So you just look at the ranking until here, and you wonder which percentage until here is relevant. So that's 100%. And now you just tell me, based on what you see on the slides, what the precision for the... So here it's 100%. You just look at the first one, and they are all relevant, or 1. Precision at 2, you look at the first 2, how many are relevant, what's the percentage? 50% exactly. Or 0.5, it's the same thing. Precision at 3, 33 point blah blah, yeah, exactly. 0.33 and so on. Precision at 4, 50%, yes. And that's one of the most common measures, really. This is very simple. Precision at 5, 60%. 3 out of... no, what is it? Precision at 5? No, it's 60. Yeah, I mislooked. 60%. It's 3 out of 5. It's 0.6. And then there's one particular precision measure. It's just precision at the position which is equal to the number of relevant documents. So let's assume we have, let's assume k is equal to 3 here. Yeah, no, I don't have to show an example. I mean, it's just the precision at, yeah, you just plug in that R and then you get that number. So if there are only 3 relevant documents, then P at 3 would be the precision at R. It would be 33%. So that's kind of the simplest number you can compute. So average precision, let's do the same thing again. So we have the, okay. So this is, yeah, let's do this. Now we have a slightly different result list. So the first one is relevant. Which other ones are relevant? Oh, I think it's very similar as the one before. We have, this one is relevant. And this one is relevant, and that's at position, and let's write down the position below here. So this is the first document, this is the second document, you list the third one, the fourth one, and the fifth one, and let's just say this is the 40th position. Let's just pretend that it is. So, yeah, one relevant document, it comes very far back in your list. So, now, when you want to compute average precision, you are asking for precision at certain positions, namely at the position where you find your relevant documents. So you want precision at 1, precision at 4, precision at 5, precision at 40. So you tell me what's precision at 1? 100%, yes. What's the precision at 4? 50%, yeah. We have 4 documents, 2 of them are relevant. 50%. What's the precision at 5, the position of the third relevant document? 60%, yes. And now, what's the precision at 40, which is the position of the fourth relevant document? 10%, yes. Because it's 40 and there are 4 relevant documents, 4 over 40, 10%. So you compute these precisions, and now you just take the average precision, which is just the average of these 4. And this is something which you will compute for the exercise sheet. And you can tell me, so it's just the average of these numbers, 60% plus 10% divided by 4. What's the sum of the thing in parentheses? 220 divided by 4 is 55. Very good. 55%. So that's the average precision, yes, just the average of these. And you see this last one really hurt us, right? 10%. So it hurts when you have a relevant document that comes very far back. Or maybe you did first for the first one, but to have a good average precision, you must not, you must take care. The question is, what is if a document is not in the result list at all? Maybe your search engine, it does, right? The search engines we wrote so far, they don't return all the documents, but just a subset, namely those for the second exercise sheet, which contain at least one of the query words. Maybe for some reason, because you don't index numbers, your relevant document, a movie, does not occur at all. And then we just do as if it would occur at position infinity, right? You already see it here, far back the number goes towards 0, so we just set it as 0, which is the same as saying it occurs at position 1 billion. So that's the border case. Then there's mean precisions, which is just, that's easy. These were numbers for a particular query. And notice, this is already an average. So that's an average over certain precisions. So it's called average precision. And now you do this for many queries, like for 11 queries. And now you want one number in the end and not 11 numbers in the end. So you compute this number for each of the 11 queries, which is already an average. And you average that over all queries. And you don't call that average precision, but mean average precision. But mean is really just a synonym for average. Yeah. And you can do that with all the other measures as well, right? You just take the average over all queries, except that you don't call it average. You call it mean. It's not mean, it's the mean. Yeah. And you will find these a lot, and variations of these information retrieval, but also in other research, very natural measures. And let's just look at the table on the wiki. Yeah, you see here, you have so precision at 3, how many of the third document, and that's something which is very important for web search, just the top hits, how good are they? We absolutely want to know those to be relevant, and then you just average that over all queries at R and also map. Map is a very hard measure to optimize because average precision is hard because now all the relevant documents have to be good. It's hard to get that high. Here are some more measures which are now a little more refined. Those were the simple measure, and that's what the rest of the lecture is about. So just 5 more slides. That's already the last part. So let's look at those. Also very popular exam questions. What's very frequent, and actually also in our example, now what's a good, let me just, yeah, I don't know, maybe, I don't know if we have Batman, for example. So you have a query which says movies about Batman. Now, what's a movie about Batman? That's maybe an ill-defined. There are movies which are really about the Batman, only about the Batman, so these are super relevant documents for a Batman query, but then there are movies which are maybe Batman is only one of several characters, right? You have many such queries where you have shades of relevant. Super relevant, like right on target, somewhat relevant, not relevant. And you can have more shades. So that's really very frequent. You have shades of relevance. And now, you certainly want a bonus to have the very relevant ones before the somewhat relevant ones, right? It should be ideal is the very relevant ones first, then the somewhat relevant ones, and then the not relevant ones. And here's a formula which does that, and here's an even better formula which does that. So now you sum up. So this is just summing up the relevance. So this is like 0 if it's not relevant, and otherwise it's this score, so a 2 for very relevant. This does not take into account the positions, right? If the very relevant one is first or 10th would not matter here because I'm summing this up, which is why I now give this discount here. I divide by the logarithm of the position. And you will see in the example on the next slide why that is a good idea. Now it helps if the very relevant ones come first. We will see it on the next slide. And that's why it's called discounted, because you now give a discount to the scores if they come later in the list. Yes, and this will be, let's first go to an example, then we understand the rest of the formula. It's always so let's do so we have a relevant one here. So now how do we start? Maybe we should, how did I call the formula on the previous? DCGG at, let's just write the formula here. DCG at 5 was just the sum from 1 to 5 of this relevance information, which is 1, 2, or 0, divided by log 2 of I plus 1. So it's a sum of 5 values now, and you tell me what the 5 values are for this list. So I have search engine returned 5 hits in that order. The order is important. First one was relevant, third one was very relevant, fourth one was relevant, the other ones not. So I now want a sum with 5 things. What's the first thing here? 1, that's correct. What's the second thing? 0, yes. The third one? 2 over? 2 over 4? It's log 2 of, we have to plug in this. 2 over 2. So so the positions are, maybe I should write the position. It's not 0 based. It's so this is the first hit. No, it's already written there. It's hit number 1. It's hit number 2. Yeah, so the I, maybe I should just write what the I is. I mean, it's just 1, 2, 3, 4, 5. So what's the denominator? 2? Yeah, it's log 2 of 4. That's correct. It's log, yeah, it's 2. Let me just write it. Log 2 of 4, which is 2. Yes. Next one is, so now we have a 1. Log 2 of 5, that's correct. And then we have a 0 again. So this is 1 plus 1 plus 1 over, what's 1 over log 2 of 5? I wouldn't say that not necessarily. have to, what's 1 over log 2 of 5? That's log of 2 over log of 5, I think, independent of the, oh my, everything is so slow here, 0.43. I hope you can confirm, tell me if it's wrong. So this is 0.43 approximately. So the whole thing is 2.43, yes? So now we have that number, but the problem is this number is not, I mean, is 2.43 good or is it bad? We should somehow, and that was the point, we haven't talked about it yet, of the other part of the previous slide, we somehow have to compute the ideal ranking. So the ideal ranking would be, and let's just put it here in a separate, so if in the ideal one we would have the 2 first, and then the 1, and then the 1, and then 0, and then 0, right? We first have the very relevant one, there's only 1, then the 2 somewhat relevant ones. And now let's do a little faster, the same sum for the ideal value. So what do we have here? First one? 2. Second one? 1 over log 2, right? Oh yeah, it's 3. You are right, I'm wrong. Log 2 of 3, another funny number. Third one is, yeah, 1 over 1 over log 2 of 4, right? Plus 0, plus 0. Okay, so we have another funny number here, which is 1 over log 2 of 3. What's 1 over log 2 of 3? 1/6. 1.6, okay. Is it? 0.63. So it's 0.63. So it's 2 plus, and this is 1 over, it's 2 point, is that correct here? This is 1 over log 2, 4, which is 1/2, right? So it's 2.5, and this here, it's 3.13. Is that correct, or did I make a mistake? Is it really 0. It's a coincidence that it's... Natalie, did I make a mistake, or does it look correct to you? Looks correct. See, it's 3.13. Okay, let's assume it's correct. Anyway, the idea was correct. So now we have, this is the ideal, and this is what we got. And so, yeah, what we can do now is just divide this by the idea. And that's how you compute the... Yes, just a second. Let me compute the final number here, and then the question. So let's just compute that 2.43 divided by 3.13, and now we get a percentage again, which is always nice, right? This is like 77.6%. Yes, please, the question.
Yes, the only punish completely wrong hits if they are in the ordering very far behind. So I understand it right? If we have hit 6 and the hit 6 has nothing to do with Batman, it won't be punished. Because it will be a 0 and we can have infinite more hits and it is not a problem.
Yeah, that's a very good question, and I come back, I think, on slide 10. What about, so right now I'm returning a list, and what about all the documents which are not relevant at the back of my list? And web search does that, right? You never go to page 200 of your web search result. If you go further down, or some people maybe do, then it becomes quite irrelevant at some point. And the question is, that was your question, I think, should that be punished? And these formulas don't punish it. But it's a reasonable question, and I have something to say about the next slide. I mean, what's behind that question is, shouldn't the search engine only give me those results which are relevant and then cut off at some point and say, no more results now. I don't show you anything else. And that's just too hard, which is why it's not done. You always do this ranked thing and you don't care what comes later as long as the relevant ones are at the top. But it's a very, very reasonable question. Are there any other questions at this point? So this was normalized discounted gain, and you see the idea here. You compute these numbers, you normalize them by the ideal, and the ideal score depends on the query, so you have to compute it for every query, but you can, and then you again get a percentage. And this is, yeah, frequent. And here's another one, and I think that's the, yeah, sure.
Regarding the ground truth, when we look back at the example for the matrix, so the ground truth for matrix would not include the John Wick movie, although it mentions matrix in the description, but only the actual matrix movies, right?
Yeah, that's a very good, another very good question. Ground truth construction. So what is ground truth? This is, and this is true also for all the machine learning benchmark, whatever problem they solve, the question is, what is a relevant document? This is something which the experts which do this have to decide, and that's, they don't necessarily agree, right? So let's go maybe to our benchmark here, which I showed you earlier. Yeah. So here are some which are kind of very objective, right? Films directed by Steven Spielberg, I think that's objective, so there's a perfect ground truth, but yeah, exactly. This is already debatable what should be in here. So this is indeed a big, there can be mistakes in the ground truth, there can be disagreements between different evaluators. For the exercise sheet, we don't have shades of relevance, it's just relevant or not, so we don't have this discounted thing. And so actually we have to ask, so Natalie, how did you decide? You did that query? How did you decide what to include when you, because actually what we did is, we looked at a larger set and then we looked at each movie and said, yeah, this is about Batman. So what did you do?
I took those movies that where Batman occurs. So also, if it's, I mean, this is a long list, so it doesn't have to be the main character.
Mm-hmm.
If he occurs, I included it. There was also a case where it was, I think it was in the test set about Sherlock Holmes. Someone was posing as Sherlock Holmes. So it's kind of, you could say it's about him, but I did not include it because it's not the actual person that's meant by Sherlock Holmes.
Yeah, so let me repeat it for the Zoom people. So you heard a longer story which somehow conveys that it's not so hard. For some movies you really have to think about it. So films about Sherlock Holmes. There was a movie where somebody was not playing Sherlock Holmes but posing as Sherlock Holmes. Now is this a movie about Sherlock Holmes? Debatable. Natalie did not include it. But yeah, very hard questions. And it's a problem for a lot of benchmarks that, yeah, there's disagreement between evaluators and even mistakes. Yeah, so it's a very valid question and a big topic for, not only for search engine benchmarks. Okay, let's move on to our last measure, and then there's time for more questions. I will again go through to the exercise sheet. That's important, not for our scenario here, also a typical exam question, but for a scenario where you have a competition. And it's again what we have here. We have now done this, Natalie has done this before, that's quite a lot of work. And now we did this for our movies collection, which was like 100,000 movies or so. I mean, you can't look at all of them, but you can kind of do exhaustive searches there. Imagine you have some much bigger collection with millions of documents. There's just no way you can find all relevant documents in that collection, right? Even for the 100,000, there's already no way. You have to use some heuristics. You have a web corpus, and there's a query, and now I want to find all relevant documents for a query. Impossible. And so in these competitions, how do you do that? And so you can actually run a competition where you don't have any relevant judgments, but you just take what the people submit. Everybody submits something, and you just say, okay, the top 3 of these engines, let me just declare them relevant. Or maybe judges look at some documents and not at others. So you have some relevant judgments, and but for some you just don't know whether they're relevant. So in the end, and let me jump to the example and then jump back to the formula, you have something like this. So your search engine returns something like this, and for some positions you just don't know what you returned, whether it's relevant or not, because the judges or telling from the other engines, we do not know whether it's relevant. So you have this situation. Not relevant, relevant, I don't know. And the question is, how do you evaluate it? So you can forget about the motivation part. If you just want it as a formal problem, it's you now also have I don't know for the reasons I just explained. And that's actually not so easy. And here, so these formulas, they always look very frightening when you look. BM25 also looks frightening, and you wonder, wow, why is that? 1 over R, sum RR, 1 minus. So, but if you look at this in detail with an example, then it becomes clear, and we will do that on the next slide. I will not explain this here. This is for reference. I will explain it by example. And then if you want to understand it at home, you can look at this yourself. So here's the example. And what you need to know is you need the example, and you also need to know how many relevant documents are they overall. So in this case, there's 1 more, so 3 overall. And how many non-relevants are there overall. So for all the others, we don't know. But we know that there are, I've just not listed them here. So there are 13 not relevant ones, 3 relevant ones. And now we want to compute these numbers, which were defined on the slide before. And RR, what was RR? Actually, yeah, okay, that's the... And let's try to understand the formula before you have seen it. So this is very simple. It's just the search engine has returned this list, and of 2 documents in that list, we know that they're relevant. So that's just this number. It's just 2. R is just the total number of relevant documents. That's also easy. So that's just a 3. There are 3 relevant documents in total. I have found 2. N is just the total number of non-relevant documents. So 13 are not relevant. That's 13. And now come these numbers. They are the interesting ones. So this now says at number 3, where I have my, let me take the mouse so that you see a pointer. What score do I give to that position? Now I can't use precision at 3. Precision at 3 would have to say, okay, among the top 3, how many are relevant? I don't know whether the first is relevant. So what this measure here does is it looks at 1 minus, let me just briefly check it with the previous slide. Yeah. It looks at how many non-relevant ones come before the relevant ones here. So I want to punish if non-relevant ones come before the relevant ones. And I want to know and the denominator is this, in this case, the minimum of R and N. I will talk about that in a second. Let's just take it for granted now. Minimum of 3 and 13 is 3. So it's just, there is 1 over, so it's just 1 non-relevant one before. And this is divided by 3. There are 3 yeah, 3 relevant ones, 30 non-relevant ones, take the smaller one, so this is 2 over 3. So 66%. And you try to understand that number, or yeah, maybe try to understand it now before we do the next one. If there would be no irrelevant one before the number 3, I would get the highest score here, right? So I get punished if non-relevant ones come before my relevant ones. If there are only question marks, they might be relevant, I don't know, so I'm not getting punished. Number 8, what do I have? And here you see the maximum punishment. I have a relevant here, one here, and 3 non-relevant ones come before me, and there are only 3 relevant documents overall. So here I get 1 minus, how many non-relevant ones come before me? 3. There are 3 relevants in total, so it's 0. And 0 in percent is 0%. So why do I get punished so much? Think about it. I have only 3 relevant documents. I don't know about the others. If 3 not relevant ones are before me, that's, I mean, in the ideal ranking, the first 3 would be at the top, right? And so I'm coming at a position, yeah, after the ones where I should have all the relevant documents. So it's kind of taken as the worst case here. I already get a 0. No, we can't. Yeah, thank you for that question, because that's exactly why do we have this min r over n. So the n is clear. I'm counting what I put in the numerator here was number of not relevant documents that come before, and the largest number for this is obviously this 13 here. So that's by dividing by n, I ensure that this is a number between 0 and 1. If I would just divide by n here and not by min r over n.
No, I'm a bit confused because if we had, for example, 6 would be not relevant.
Yeah, I'm also confused now. Yeah, I was just, yeah, you're right. So now I'm, okay, let's look at the formula and see what I did.
The write-up was a bit confusing because NR had 3 just be 1, and NR of 8 should just be.
Say it again.
The write-up on the next slide is a bit confusing because NR at 3 should actually just be 1. That's how it's defined. NR at 8 should just be 3.
Oh, you're saying it should not be the 1 minus thing? Yeah, I'm sorry. I confused that. Okay, the NR is not the 1 minus thing. Okay, but I can fix that by, yes. Oh, yeah. Okay, I took the NR for the whole thing. Okay, we will come to that. Okay, so this is not actually what I wrote here, but I think we can fix it this way. I'm sorry. Yeah, but making mistakes is great because you usually learn something. And tell me if this is now right. So this is now what I actually computed here was 1 minus NR of number 3 divided over the min. Is that correct, Natalie? I think so. And so I already wrote not the NR thing, but and now to your question. And I think there is a... Now you said that, and you are absolutely right, there could be 5 relevant, non-relevant documents here, and then I would have 5 over 3, and then it could become negative. Now let's look at the subtle detail, what it says here. Okay, so I have, I'm just looking at the top, at the R top ranked non-relevant ones before. So yeah, so I'm just cutting it off. I'm just looking at the 3 top ranked not relevant ones. You see there are a lot of subtleties in that formula. So if I would have 5 non-relevant ones here, before that relevant ones, I would just take 3 of them and not so. Yeah. That's just how it's defined, and it's defined that way obviously, so that this is a number between 0 and 1. Okay. So to summarize, I mean, it's actually, if you look at it, there are simple reasons for each of these components of the formula, but simple things in combination very quickly give something complex to understand. Let me just summarize. The reason for the n is, that's just natural normalization here, and the reason for the r is to punish it more, right? If you just have 3 relevant documents, you already get a 0 here if you just have 3 not relevant ones before. You wouldn't need it technically, but it just makes it harder to get a good score. So you get a 0 pretty quickly. And then the bpref is just the average of these, yes? So it's just the average now over. Okay, but now you're just taking so it's just 0 plus. But it's now not the average over all, but I think just over, yeah, over the 2. Oh no, but you're dividing by r, so you're making, yeah, anyway, for the other one you get a 0. So it's a really hard score to, let me write that. So what I'm now doing is I have 3 relevant documents. For the third one I get a 0 because it's not even in my list, so I'm getting let me just write the fractions here. 2/3 plus, here I get a 0. It is in my list, but so many non-relevant ones come before. And I get a 0. I don't get a 0, but I just write it here as a 0 because I divide by 3, which means it gives 2 over 9. And how much percent is 2 over 9? What's 1 over 9? Doing fractions in your head is also a good exercise against anything. 1 over 9 is? What? 11, yeah, 11.1111. Yeah, so it's 22%. Exactly. So you see, pretty bad, because, yeah, the first one was okay, but this one already gave me 0, and this was not even in my list. Yeah, so it's hard to get a good bpref. Okay, so we are coming to the end. Overfitting, yeah, that's important. Let me just repeat what I said earlier because it's so important. It's also written on the exercise sheet. Oh my, this is so slow on this machine. So, of course, if you play around with a benchmark, it's trivial to achieve a perfect result for that benchmark. You could just write a program that says if query equals to this, then output this. Yeah, that's not a search engine, that's extreme overfitting. If this, then output this. You just fix the output for the results in your benchmark. You shouldn't do that. So what we have here is this training and this test set. And let me just go to the exercise sheet and please read it carefully. There are subtleties here. So you get the training benchmark. This you can look at as much as you want and tune around with your engine. And you can also modify the queries. Yeah, just take what's written there as a description. So you don't have to, you can change the query, right? You can just say Stanley Kubrick director or directed or whatever you like. You can choose the query words. That's just here the description of the query. Do all that with a training benchmark. And only when you are done, when you have fixed your parameters, I will take this K, I will take this B, I will boost things in the title, I will do this and that and whatever. Now, and also on your test benchmark, this is the test benchmark. You can also think about how will I pick my query, like I just said. But you have to pick it, and now it's fixed. And now whatever you have now you run it on your test data set, and now you enter it in this cable, and then you are done. So you're not allowed, of course we can, I mean, it's just a game, it's a fun competition, But then you shouldn't go back and say, I think I can still do better. Let me tune this a little bit. Then you are starting to overfit. Yes?
Are we allowed to redefine words like that we include, for example, white spaces into words and have word combinations as new words?
Okay, so you want to redefine words. Can you give an example?
For example, that I say that one of my words is directed by with the white space in between.
Okay, what you want to do is like phrase search. You want to take positional information into account, which is very important. Like you have directed by, you are asking that, and you only consider it a match if the words are nearby in your document. Yeah. And you could do that in several ways by including positional information in your index and just giving higher score if the values are close together or even nearby, or by merging these words. You are free to do whatever you like to. I mean, it's more work, of course, but yeah. And if you think about it further, there are millions of ideas gradually becoming more work to implement, but yes. And there's this, here it says refinements, so yeah, if you want, you can write you can write a long entry here if you try out a lot of things. But yes, so let your fantasy run wild. You're very welcome to. And here's some, so we are almost done. Yeah, that corresponds well to an earlier question. So this is almost a philosophical question. It's so great to close, Wort zum Sonntag. So if you think about it, it's a bit strange, right? We are giving you the ground truth as sets, or as, no, not as, sorry. Yeah, it's a set. We are not saying in which order they should, I mean, we are treating them as a set. Here it's a sequence, but we are not saying 57 should be first or something. We are just saying this is the set of relevant documents. All our measures consider this as a set. So sets of relevant documents, but your engine returns a ranked list. You're comparing a ranked list against a set. And this immediately leads to the question, okay, shouldn't my result be a set, or shouldn't my ground truth be a ranked list or a ranked set or whatever? And this is just some food for thought. We could discuss this forever, but well, search engines, why not let them output a set? Yes, you could try to, but the simple answer is just that it's super hard. If you would choose a cutoff, you're always in danger of cutting off too much, and it's just, yeah. It doesn't hurt if you have things further down in your list which are irrelevant, because people don't look further down in the list anyway, but for those few who want, you better show it in case you have a relevant one at position 100, so that you can find it if you're really up to scrolling down the list. So that's the reason why search engines do it. Why isn't our ground truth also a ranked list? Well, that can, I mean, you could give, yeah, here you couldn't do it, for example. Films directed by Stanley Kubrick, these are just the films, they don't have an order, right? Now you would have to say which films are better or something. You would need popularity measures. That's a different query then. I mean, they don't have a natural order. Sometimes you have these shades of relevance, we talked about it, but you don't really have a full order, right? And then the third question, which you might also wonder, why don't we give the thing scores? And you compare actual scores. So you say this should get a 0.8. Well, we also had that earlier because you're asking such great questions. The absolute scores don't really mean that much, right? The scores in these engines, which is also why they're not usually displayed, they are just vehicles to get a ranking, right? You could multiply all scores by a factor of 2, you get the same ranking. The absolute values of the scores don't mean much. In the early days, Google would show their page rank, their Google's internal score, but they don't do that anymore for a long time. So that's it for this lecture. quickly go to the exercise sheet. I think I explained everything. So a lot to play around with. There's a minimal version. If I'm correct, you have 2 weeks, Natalie, is that correct? Yes, you have 2 weeks, which means you don't start in 2 weeks. You should start now. Absolutely, if you have problems or if you have no problems, at least start now, that you have started, that you know what it's about, maybe continue later, but always take the motivation and inspiration from the lecture, start immediately, then make a break, finish later, that's okay. Don't make the mistake of only starting in 1.5 weeks. The Q&A session is not on this Friday, but Friday in a week, just for all the accumulated problems. Is there any question right now left over? Does not seem to be the case, so have fun working on the sheet and see you again in 2 weeks. Bye-bye.